will be particularly either familiar or potentially quite useful because we're going to be talking about vectors, specifically 2D vectors. We're not going to do all of the Chapter 8 materials that I've posted. Really just, stop talking, please. Probably like the first 2.5-ish sections of the Chapter 8 materials that I've posted, but that's probably about right. All right, so we're going to start by talking about 2D vectors today. So let's start by definition. So a vector has two quantities that describe it. Those quantities are magnitude and direction. So for those of you in physics, can I just have a quick little head count on the people that are in physics? How many of us? Okay, so the majority of us. Those of you that aren't might be taking it next year. It looks like a lot of the juniors didn't raise their hands. So an example of a vector description might be like a 10 Newton force is applied at 45 degrees above the horizontal. So when we draw this, if this is like our horizontal here, the vector we're going to draw is like an arrow, where the length of the vector represents its magnitude, and the angle here, relative to the description, is going to represent its direction. Typically, we name vectors with like a single letter, and then we put a arrow on top of it to denote that this is a vector quantity as opposed to like a variable, like a scalar quantity, something that doesn't have a direction component to it. So let's call this vector that I've drawn here vector v, and we draw it with a v with a little half arrow above it. If you draw a full arrow, that's fine too. And I'll try to be careful about making sure I'm denoting vectors with arrows and scalars with non-arrows. Oftentimes in print, and this is the case in our textbook, then rather than putting the arrow on there, they'll boldface a vector quantity as opposed to a scalar quantity. So if you see a bold-faced letter, what they're talking about is a vector there as opposed to just a scalar quantity like 5 or something with no direction associated with it. All right. Now, more common, especially in a mathematics classroom, is rather than describing the vector, just giving its magnitude and direction, is to write that vector in something called component form. So we'll write our vector in component form as we use these wedge-shaped brackets, and as opposed to a parenthesis there. So very important that you're using that notation, not using it as a parenthesis, because this is not the same as an ordered pair. And then we'll have two scalar values inside of that component form. So the A and B are called the components of vector A, or vector V in this case. And what this represents So when we talk about the initial point of the vector, that's like the tail end of our arrow. And we talk about the terminal point of the vector, that's like the head of the arrow. So for example, if we have the vector v as 2, -3, and I wanted to draw that, so the initial point here at the origin, and then I go 2 to the right and 3 down. So that's what my vector v would look like. Everybody okay with that idea? Okay. And we'll talk about how to take something in component form like this and tease out its magnitude and direction, and similarly how to take something that's given as a magnitude and direction, put it back into this component form, because it'll be useful in manipulating these vectors to be able to go back and forth between these two different representations. But that's as much as I want to do at this exact moment. We haven't gotten quite to going back and forth. There's still some more vocab to do before that. But think of these as two separate representations, right, that describe the same thing. Okay? The way I'd like you to think about it is, so let's say your house is here and your friend's house is here. So one way you could go to your friend's house is just take a direct path, right? The other way you could do it is you go like up and then over, right? Everybody can kind of see that those are both reasonable ways to get to your friend's path or friend's house. Everybody agree with that? And they're related, right? How are they related? Well, if that's a right angle, and those are lengths, they're related via the Pythagorean theorem. So we can use what we know about right triangles to go back and forth between something that's like a component form, which would be like this, and something that's kind of in that other vector representation where you give a magnitude and direction, which is like that arrow. And it's basically just doing like trigonometry, SOHCAHTOA, to go back and forth between them. But we'll do some more of that with numeric examples here shortly. Okay? But there's still some more vocab that I'd like to do. All right. So the magnitude of a vector, come in. Hello. Thanks. Olivia, it's for you, I'm guessing. They had only your last name on this, though, which is quite mysterious. So the notation that we're going to use to represent the magnitude of the vector, so for vector v, the magnitude of vector v is written as that. So where have you seen those two vertical bar symbols before? Absolute value. And maybe some of us from your Algebra 3-4 class, when we talked about matrices, remember it as a determinant. We use that symbol there as well. Here's a third different way that we're using these vertical bars. So how can I tell in this representation that we're talking about a magnitude as opposed to absolute value? Because there's a vector symbol inside of it. Yes, very good. Okay, so if I see that the vertical bars are surrounding a vector, I know that I'm not talking about absolute value. Okay, if the vertical bars were around a single number, now we're talking about an absolute value, right? If the vertical bars were around a matrix, then we'd be talking about a determinant. Yes?
So is it those bars of vector is equal to the magnitude, or the magnitude?
So this will give you the magnitude. We haven't talked about how to find that yet, but that's just the symbol that we're going to use. So just a lot of vocab and notation right now, because this is it's a different language that we're speaking, right? Because a vector quantity is fundamentally different than like just a number, because we have this extra direction part that we have to describe. Okay. So the next thing I want to talk about is called the head minus tail rule. I'm going to abbreviate that as HMT for head minus tail. So if I have a vector v that has the initial point x1, y1, and a terminal point x2, y2, then the component form for vector v is just going to be x2 minus x1, comma y2 minus y1. So what are we really doing when we're taking that vector and putting it into component form? Let me do something like that. So let's say this is my vector v here. This is also vector v. Notice here, is the direction the same? Right? The arrows are pointed at the same angle, right? Is the length of the vector the same? Yeah, they're the same length. What's the only thing that's changed? Basically just picked it up and moved it to a new location, right? But we preserved the angle and we preserved the direction. So are these two still the same vector? Yes. Does everybody kind of see that? So that's all we're doing when we're taking something from and putting it into component form, is just translating that vector so its initial location or initial point is at the origin, but we're preserving the length of the vector, we're preserving its magnitude, and the direction, the angle that it makes relative to the x or y axis, still maintained. Is everybody okay with that idea? Okay. So, keeping this in mind now, we can ask questions like, or we can do things like the following, I guess. So here we're asked to show that the vector from 3, -2 to 5, 1 is equivalent to the vector from -1, 2 to 1, 5. So to show two vectors are equivalent or equal, I would need to show that they have the same magnitude and the same direction. Or, what's going to be massively easier in this case, I can just show that they have the same component form, right? If they have the same component form, then they're obviously going to be the same vector, right? Is everybody okay with that idea? So I'm just going to take my vector that I'm going to name the first one AB. So that would be x2 minus x1, y2 minus y1. And then if I take vector xy, x2 minus x1, y2 minus y1, and I get the same component form. So since these two vectors have the same component form, they have the same magnitude and direction, and that implies then that they are equal. So rather than finding the magnitude and direction of each of these two vectors independently, which we could do, but we haven't talked about how to do that yet, it would actually be a lot more work in this situation. We can work around having to do that by just showing that they have the same component forms. Scroll up there for the people bobbing and weaving back there trying to read what's there. Does everybody feel okay on this idea? So that's an easy test if you're given the initial and terminal points for two vectors to see if the two vectors are the same, put them into component form and just compare the components. So here's our definition of how to calculate the magnitude given the initial and terminal points for our vector. Does anybody recognize this formula from geometry? This is just the distance formula, right? This is how we found the distance between 2 points in the xy plane. And if magnitude is just the length of the vector, we have where it starts and ends, the distance formula will obviously give us the length for that vector, right? What happens if we've written the vector in component form? What does component form mean again? Can we write the vector with the wedge like this? Means the initial point of our vector is the origin, and the terminal point of our vector is AB. So if I use the formula from above, it just simplifies down to a squared, or the square root of a squared plus b squared. Since the initial point is the origin, the x1 and y1 basically vanish, right? From the formula above. What does this now remind us of? Also from geometry, this looks a lot like the Pythagorean Theorem, right? A squared plus b squared is equal to c squared. So c is the square root of a squared plus b squared, which is what we see right here. Everybody okay with that? Hopefully it's becoming clear why we're spending time inside of a trigonometry / pre-calculus course talking about vectors, is there's a lot of relations back to these triangle situations. So let's say I want to find the magnitude of the vector u that's written in component form, -2, 5. Well, it's not too bad. -2 squared is 4. 5 squared is 25. 5 plus 25 is 29. So we have then the square root of 29. Notice that 29 is a prime number. So I know immediately that I can't simplify that square root any further. Is everybody okay with that? Worth pointing out here that this is not equal to the square root of 4 plus the square root of 25. You cannot ever break a square root at an addition or subtraction symbol. So that square root symbol does not distribute. Okay, so keep that in mind. That's a common mistake I see students make. Just wanted to point that out here, especially in a situation like this where you have two perfect squares. Very tempting to say, oh, let's just square root each of them and be done. Does not work like that. Kendall. The wedges. The wedge bracket tells you that it's component rather than a point. So we use the parenthesis for an ordered pair. That's a point. The component form of a vector is the wedge brackets.
So if we were given like two separate
the other formula, yes. And let's do that here. So in this problem, we're given that vector v is the vector CD, where C is 4, -6, and D is -3, 1. So x2 minus x1 plus y2 minus y1 -7 squared is positive 49, and then positive 7 squared is also positive 49. When I add those together, I get the square root of 98. Now, 98 is an even number, so immediately I know that it's not prime. So this potentially could get cleaned up a little bit. Might be able to simplify this a little bit more. So what I'm going to do is I'm going to rewrite this as 2 times 49. 98 is 2 times 49. And that's a great outcome because I noticed that 49 is a perfect square. So I can break a square root with with multiplication and division, not with addition and subtraction, but it is okay to break a square root with multiplication and division. And the square root of 49 is just 7, and kind of the convention is we put that number in front of the square root. Everybody okay with what we did there to simplify that? Remember doing that last year a little bit in your algebra course? Hopefully. I taught most of you your algebra, so I know we did it. I don't know if you remember it, though. So what if we wanted to find the directions? So to find a direction, what we're going to do is we're going to use kind of what we know about inverse trig functions. So let's look at an example here to kind of illustrate that. Everybody okay with this? So notice that this vector is written in component form. So the first thing I'm going to do is draw myself a picture. So the vector I'm drawing is there. Everybody's okay with that? So the direction, the angle that I'm looking for is this, right? So what I'm going to do is I'm going to think about this as a right triangle. So this side length is 3 because we went 3 units to the left. And that side length is 4 because we went 4 units up. Everybody's okay there. And what I'm going to do is I'm going to find this angle here that I'm going to call theta. And then to find this angle, which I'll call alpha, it's going to be 180 minus theta. Can we see why it's 180 minus theta? So I know here to here is 180, and then I need to go backwards that theta. Does everybody see that? That's why it's going to be 180 minus theta there. Okay. Oh boy, didn't mean to erase that part. All right, so how do we find theta then? Well, because I know the opposite and adjacent side of that right triangle, I can use tan inverse of opposite over adjacent. And if I type that into my calculator, making sure that I'm in degree mode here real quick. Yep. I get 53.1 approximately for theta. So then my direction, what I'm actually looking for, 180 minus 53.1. Gives me 126.9. Everybody okay with that? Okay. What would happen if instead of giving you in component form, we give you the initial and terminal points for the vector? Well, what I would do is I would just start by putting this into component form, and then I'll do it exactly like I did the previous problem, right? It's easy to put these things in component form. So x2 minus x1, comma y2 minus y1 -8, -7 is down here. I'm not going to draw the tick marks just because there's too many of them. But I went 8 over and then 7 down. This is my angle theta. So to find my direction, I'm going to do 180 plus theta. Right? Here to here is 180 degrees, and then I need to go theta more. Everybody see why we're adding theta this time instead of subtracting? The way I think about the easy way to tell whether you should be adding or subtracting is if the how do I want to say this? Okay, so if the axis you pass before you reach the terminal side of your angle is the x-axis, you're going to be adding. That's what happened here, right? So on my way to the terminal side, I pass the x-axis right before I get to the terminal side. Here we're adding. In the previous thing, if we're passing the y-axis right before we reach the terminal side, in those cases you should be subtracting. Does that make sense to you guys? So that helps a little bit in terms of like how you know when to add or subtract. Yes? We can do that. Well, we'll mention that again. But we still have to finish this problem up here. So let's do that right quick. So theta is tan inverse of opposite over adjacent. If I type this into my calculator, I get 41.19. So my angle alpha then, 180 plus 41.19 is 221.19 degrees. Oops, 221. Thank you. Okay, so the last thing I want to talk about here today is about resolving a vector. That's when we go from magnitude and direction to component form. So if I've written my magnitude as that, and I'm going to call my direction theta, we have this formula. Magnitude times cosine of theta is our x component, and magnitude times sine theta is our y component. And this completes our ability to go back and forth, right? We just talked about the two ways, or how to go and retrieve the magnitude and direction from something in component form with the previous two examples. And with this formula now we can go from magnitude and direction into component form. So for example, if we're given that my direction is 224 and my magnitude is 5, I can then say the component form is going to be 5 times cosine of 224, comma 5 times sine 224. And when I type that into my calculator, I get negative 3.60, negative 3.47, rounded to 2 decimal places. So again, just to kind of sum up what we did today. We've talked about how to go back and forth between these two forms. So this one, we did this is what we just did a second ago. So that's kind of what to summarize visually, what we've just got done discussing today. It's hard to, there's not like a specific formula here for direction because you have to draw that picture and then decide whether you're adding and subtracting. And then whether it's going to be 180 or maybe it's 360 or whatever. But usually that number is going to be 180 there. Could be 0 as well. So if you go to your PowerSchool page,